All right, hello and welcome to another Jamovi tutorial. Today we're going to be tackling regression. This is our first tutorial on regression, and we're going to be covering something called a simple linear regression. I have the data set that you can use to follow along linked in the description below, so I highly recommend that you open that up in Jamovi on your own computer or device and that you follow along with me so that you can click all the same things I'm clicking and really get a good idea of what's going on with the data. So by the end of this video, you're going to know how to run simple linear regression in Jamovi, including how to test those assumptions and make sure that they've been met. And importantly, I'm going to walk you through how you can interpret the output, because there is quite a bit of output with a simple linear regression, and I want to make sure that you know what all of that different information is. So open up your data set and let's get into it. All right, so we're going to start with the basics. What is a simple linear regression and what kind of situation will we be using it in? So a simple linear regression is a statistical model that helps us to predict one continuous variable, the outcome, based on another continuous variable called the predictor. So the example that we're going to be working with is we want to predict an athlete's sleeping heart rate from the drug dosage that they're taking. So imagine that we're running a study on a new experimental drug for athletes, and we want to know, does the dosage of the drug predict the athlete's heart rate while they're sleeping? This is the perfect situation for a simple linear regression because we have two continuous variables. You might recall from previous videos with t-tests or ANOVAs, one of the variables that we're working with typically needs to be not a continuous variable. It needs to be nominal or binary in nature. But with regression, we can have two continuous variables, which gives us a lot of flexibility in the kinds of research questions that we can ask. So in this case, we have our predictor variable. This is also known as the end-dependent variable. And in this situation, that's going to be the drug dosage. The outcome variable here, also called the dependent variable, is going to be the person's sleeping heart rate. Regression is nice because it lets us quantify relationships and then also make predictions. If we find a strong relationship, then we can estimate how much an athlete's heart rate will increase or decrease based on different drug dosages. So let's go ahead and open up our data set in Jamovi so I can show you how you can ask this question and analyze the data there. So first you're going to go to analyses, and then you're going to select regression, and then you're going to select linear regression. You should see the data set open up for you, and we are going to move sleeping heart rate over to the dependent variable box. That's what we're trying to predict, or that is our outcome. Our predictor here is going to be the dose manipulation of that experimental drug. So we're going to move that over to a box called covariance. You'll see in Jamovi that with regressions, and we'll get more into this in the multiple regression video, you can have variables in the model that are continuous, like we have today with our simple linear regression, and you can also include variables that are not continuous, that are nominal or ordinal in nature. And so those go in the factors box. So we're just going to be sticking to that covariate box for now. Then I'm going to have you move down to assumption checks. So we've discussed this in previous videos, but assumptions are a set of standards that our data need to meet before we can fully interpret the results of our analysis so that we can make sure that that interpretation is indeed accurate. With a simple linear regression, we have a couple of assumptions. So we have our assumption of independence, which we've talked about in every video. And that assumption states that each of the data points are independent of one another. This is a very important assumption, and it is one that we typically deal with outside of Jamovi. So if you're an experimenter and you're creating your study and you're collecting data, that's when you'd want to be really careful and mindful that all of your data points are independent from one another. There are some ways and some more advanced analyses like structural equation modeling and things like that to take a look at independence once you're in the analysis portion, but that is well beyond the scope of the purpose of this video. So just know independence is important, and probably you'll be addressing that before you get into Jamovi. Now, there are some assumptions that we do need to check in Jamovi. So if you take a look at your assumptions test, the first one that I want to point you to is normality. So in Jamovi, one of the cool things about Jamovi is that it's always updating, and people are creating packages that you can add on to make your software even more capable. So if you look up in the corner, there should be a button that says modules. And if you click on that button, you can add different add-ons that people have created to make Jamovi even more flexible and be able to do more things. So I highly recommend going to that and typing in more tests. That is an add-on module that allows you to have access to even more assumption tests, which makes checking assumptions specifically for regression even easier. So first I'll talk about normality and then I'll talk about the next one. But when you click on normality, you'll notice if you have the add-on module for more tests that you've got not only the Shapiro-Wilk test, but other tests for normality as well. We're going to stick with the Shapiro-Wilk test. And the rule of thumb here is that we want the p-value associated with that Shapiro-Wilk test to be greater than 0.05. This tells us that we have met the assumption of normality. If the p-value is less than 0.05, that means that our data's normality is statistically significantly different from what would be normal. And we don't want that. We want our data to be normal, which means we don't want a statistically significant p-value here. It looks like our p-value is well above 0.05 for this normality test, so we are good to go. Now, one of the other important assumptions with regression is something called heteroscedasticity. This is sort of similar to homogeneity of variance. It takes a look at a plot of your data. And the way that we used to have to test this, if you don't have the more tests option, is by looking at residual plots, which you can click on. And you'll see Jamovi, when you click on residual plots, will give you a series of plots. And what we're looking for here is that these plots of the data are roughly rectangular in shape. We want the variability basically to be consistent across the whole plot. However, there's a lot of room for error here because just a person is visually assessing and saying, yeah, that looks roughly rectangular, right? When do we know when it's rectangular enough or when it's not rectangular enough? So my students and myself have always really not liked having to just use a visual examination in order to test if this assumption is met. That's where the more test option comes in, because if we scroll up again, you'll see that when you click on the normality test after you've added the more tests module, you get heteroscedasticity tests and an associated p-value. This makes our life so much easier because we can just take a look at that p-value to determine if we have met or violated the assumption instead of relying on a visual assessment of the plot. So we're going to take a look at that Breusch Pagan statistic. And again, we want to make sure that that p-value is greater than 0.05 in order to determine that we have met the assumption. Here, our p-value is indeed greater than 0.05. So we now can confirm we have met the assumptions of normality and heteroscedasticity. Another assumption that you're going to want to take a look at is the assumption of linearity. So this assumption states that the predictor and outcome variable are going to have a linear relationship. So in order to check this, you're actually going to go to Analyses and then Explorations and select Scatterplot. You're going to move over the sleeping heart rate to the y-axis and then the dose manipulation of the experimental drug into the x-axis. And what you're looking for here is to see that that scatter plot does indeed show that the variables have a linear relationship with one another. So we can see that here and determine that that assumption of linearity has also been met. All right. So we've met our assumptions. Now there are a couple other things that I want you to click on as you go through the options here in the regression dialog. So you're going to click on model fit, and R and R squared should already be clicked for you, but if not, go ahead and click those and then also ask for the adjusted R squared and the overall model test. Then I'm going to have you go to model coefficients, the next tab down. I'm going to have you ask for the estimate and the standardized estimate as well as the confidence interval for the standardized estimate. Once you have all of those clicked, now we can start to think about what all of this output means. So I'll work through it with you. We'll go back to the top and we'll work table by table. So the first table that you're going to see is going to be something called model fit measures. This gives us information about the effect size of our model and the overall model test. So whenever we're working in regressions, we can have multiple variables, if we'd like to, that are predicting a single outcome. Now, in this case of simple linear regression, we just have one predictor and one outcome. But this is helpful to know when we get into more complex things like multiple regression, which we'll talk about in the next video. So what this information is telling us is if the predictor or predictors that are in our model are statistically significantly predicting the outcome. So in this situation, does the dosage of the new experimental drug, does that effectively predict the heart rate of the athletes while they are sleeping? So you'll notice some familiar faces here. If you've seen the ANOVA videos, we have an F test here. So we have an F, degrees of freedom, and an associated p-value. And that's because ANOVAs and regressions are both F tests. They both are in the general linear model. So even though they're different, there are quite a bit of similarities under the hood, so to speak. So this p-value here tells us, is our model statistically significant? And again, we're looking for p-values that are less than 0.05. We have a p-value of less than 0.001. So we could say, yes, our predictor of drug dosage is significantly predicting our outcome of sleeping heart rate. So then we have a couple of other pieces of information I want to key you into here. So we have something called R squared, which is quite literally the correlation, or R, between the predictor and the outcome, and we square that value to get the effect size. And that is interpreted as variance explained. So this R squared value is 0.737. So in order to interpret that, you would move the decimal point over 2 places, and you would interpret that as 73.7% of the variance in sleeping heart rate can be explained by the drug dosage. However, that value of R squared is often biased upwards. And so I had you select the adjusted R squared, which controls for that a little bit and just gives you a slightly lower value to control for that bias. So what I would have you use to interpret the true effect size is that adjusted version of the R squared, which you'll notice is just slightly different and slightly smaller. Instead of 73.7%, we're looking at 73.5% of the variance explained. So that's our first table there. Our next table gives us something called model coefficients. So this takes that overall information that, hey, this is the effect size and the p-value of the model overall, and it starts to break it down a little bit to tell us a little bit more about what specifically is going on with our predictors. So in this situation, again, with a simple linear regression, we just have one predictor, which is the dose manipulation of the experimental drug. So one of the first columns that we have here is the estimate. So this is one of the coefficients. So this coefficient in particular is the slope of the regression equation. It tells us how much each unit increase in dosage raises heart rate. So in our situation, we have a slope of 10.8, or the estimate is 10.8. So that means that each unit increase in dosage is going to raise heart rate by 10.8 beats per minute. So you can see there that the estimate is still in the units of the original measurement. So if the original measurement is heart rate in beats per minute, then 10.8 is 10.8 beats per minute. So when we are thinking about our regression equation, we would sub in that estimate for the value of B, or for our slope. The other thing that I can point you to here is the intercept. This is the y-intercept. So if there were no drug dosage at all, the y-intercept tells you what the person's heart rate would be when they were sleeping. So in this situation, our intercept is 50.8. That means that if the person was taking no drugs at all, then that would mean that their heart rate while they were sleeping would be 50.8 beats per minute. Then if we scroll along, we've got the standard error for that estimate. We have a confidence interval. It's always good to provide additional information about the variability, so the confidence interval can help us with that. The estimate is just an estimate, so we know there's error associated with it. So for example, this 95% confidence interval for the estimate for the experimental drug, it tells us that for every additional increase in the drug, the estimate is about 10.8 beats per minute, but the confidence interval says that's just an estimate, but it's more likely to be somewhere between 9.7 and 11.8 beats per minute, for example. Then we have a value of T and a p-value. This p-value here is going to tell us if that predictor is statistically significant or not. Now, because we're working in simple linear regression, we had an overall model p-value that was less than 0.05. So we knew that if our model is statistically significant, we only have one predictor, we know that that predictor is going to be statistically significant. However, when we go into multiple regression and we have multiple predictors, sometimes you can have an overall model that is statistically significant, but not every single predictor is statistically significant. So here, this doesn't necessarily give us new information, but it is still good to know. Then again, we have another estimate here, and I want to specifically point you to the difference between the estimate and the standardized estimate. So the estimate is in the units that the variable was initially measured in. So 10.8 beats per minute, right? The standardized estimate takes that value and puts it into standard deviation units. So 0.859 standard deviations. Now, this is important, especially when we start adding more predictors into the model, because let's say we're comparing two different predictors that are measured on totally different scales. Like maybe we're predicting sleep based on heart rate and then also maybe based on income. Well, 10.8 beats per minute. How do you compare that to something that is measured in dollars, right? They're completely different scales. So how do we figure out which one is more? Well, if we turn things into standard deviation units, so they're all nice and standardized, that helps us to see which of those predictors is contributing more strongly to the model. So that's where that standardized estimate comes into play. Now, I want to return just for a moment to what all this means for the regression equation. So our regression equation is y equals bx plus a. Y is going to be our outcome variable. In this situation, that's going to be sleeping heart rate. B, again, is going to be our estimate. In this situation, that's going to be 10.8 beats per minute, which we're going to multiply by each additional drug dose that the athlete takes. So that's where our X comes in. And then finally, we have A, which is the value of the Y-intercept. So the Y-intercept here is 50.8. So if we plugged all that in, our regression equation would read sleeping heart rate is equal to 10.8 multiplied by the drug dosage plus 50.8. So to find out the athlete's specific sleeping heart rate, to try to predict that, we would just plug in the manipulation of the drug dosage value and finish out the algebra to get the sleeping heart rate. Key takeaways from this video so far. Simple linear regression predicts one continuous variable from another. The R squared versus adjusted R squared shows the variance explained, but adjusted R squared is going to be more accurate because it controls for some bias. The F-test tells us if the model is statistically significant. In our case, P is less than 0.001, so our predictor is useful. And then finally, as a reminder, standardized versus unstandardized estimates. Unstandardized are the real-world interpretation, so beats per minute increase, whereas standardized makes it easier for us to compare across multiple predictors, which we'll get into in the next video. So that is how you run and interpret a simple linear regression, including checking the assumptions. If you have any questions about how to do other things with regression or anything that you need to clarify, you can let me know in the comments below, or you can reach out to me at ajoytoteach.com, and I'm happy to work with you there further. Thanks so much.